My name is Anastasios Kyrillidis, and on this poster I'm going to talk about dropping convexity for faster semi-definite optimization. Okay, the problem we are looking for is the following. Consider the following convex problem where we try to minimize a function f subject to PSD constraints. Okay, now the main assumption and common assumptions we make for this problem and the setting that we're considering are the following. We want the function f to be Lipschitz continuous, to have Lipschitz continuous gradients, and in some cases it can be also be strongly convex. This is the only assumptions we make. Okay, there are many problem cases where we actually looking for a low rank solution to this kind of problems. What I mean by that, there are cases where actually the actual solution is low rank, or there are cases where due to computational restrictions, we want to look for a low-rank solution, because to solve this problem, for example, there are many cases where you just do projected gradient descent, and the projection onto the PSD cone is actually quite expensive. Okay, and there are also some statistical reasons where you're looking for a low-rank solution, because you might prevent overfitting in some machine learning problems. Okay, some examples are matrix completion, phase retrieval, and I will show at the very end the quantum state tomography problem. Okay, now by having low rankness and PSD constraint at the same time, we can exploit the following fact from linear algebra, that a matrix X which is rank R and at the same time is PSD can actually be written in the factor form of UU transpose, where U here is a tall matrix which has dimension n by R. What we gain by that, actually, by only working on the U space, we actually save a lot of memory. We have to maintain fewer variables to optimize on. And even in the case where U is actually, the R here is actually n, you actually substitute, so to say, the PSD constraints projection with a matrix factorization. So to wrap it up, what we're trying to do is, instead of solving the original problem, we're actually trying to solve a non-convex formulation of this problem, where we try to minimize a function g of u, where u is actually of dimension n by r, and we don't have any constraint on the PSD cone. Okay, how we're going to solve, what are our contributions? We try to solve it through gradient descent. We actually call it factor gradient descent, and what we can show is that by having a novel step size ITA, this simple and easy to implement algorithm can have local convergence guarantees, in the sense that it can have linear convergence when the function f is smooth and strongly convex, and sublinear convergence when the function f is just smooth. And we can also guarantee global convergence when we have a good initialization point. That's it. Thank you very much.